Buenas tardes, noches. Vamos a iniciar el cuarto ciclo de conferencias de Astrofísica y Cosmología, la ciencia del cosmos, la ciencia en el cosmos. Hoy tenemos la primera conferencia. La conferencia inaugural la va a impartir el profesor Willy Benz de la Universidad de Bern, en Suiza. Tratará sobre cometas y planetas y nos contará resultados recientes obtenidos con la misión Rosetta. El profesor Willy Benz es catedrático de la Universidad de Bern y director del Centro Nacional Suizo de Competencia en Investigación Planet-ES. Este es un centro de excelencia suizo en donde realmente el énfasis es uno de los primeros con un énfasis muy fuerte en lo que es la investigación básica. El profesor Willy Benz inició su carrera con su tesis doctoral que presenta en la Universidad de Ginebra en 1984. Después realiza estancias postdoctorales en el Laboratorio Nacional de Los Álamos y en la Universidad de Harvard en Estados Unidos y desempeña tareas docentes en la Universidad de Arizona y de Ginebra hasta 1977, cuando se incorpora como profesor a la Universidad de Bern. Ha recibido numerosas distinciones y premios, como el Milton Fan Award y el Thomas Temple Hobbs Prize de la Universidad de Harvard. Desde 2007 es miembro científico externo de la Sociedad Max Planck y ha sido presidente de los comités científicos más relevantes del Observatorio Europeo, del Hemisferio Austral y de la Agencia Espacial Europea. Ha publicado más de 190 artículos en revista de alto impacto, con más de 13.000 citas. Es un experto mundial en la modelización y simulaciones hidrodinámicas, que ha utilizado para entender procesos que tienen lugar en una amplia variedad de problemas astrofísicos de gran importancia en nuestros días. Ha estudiado temas tan variados como explosiones de supernova, binarias degeneradas, binarias de rayos X y fragmentación de nubes moleculares, en donde se forman las nuevas estrellas y alrededor de esas estrellas se forman los planetas. Desde el descubrimiento del primer exoplaneta en 1995 por Didier Queloz y su director de tesis, Michael Mayer, se ha dedicado a comprender la gran diversidad de exoplanetas y sistemas planetarios observados en nuestras galaxias, los cuales difieren enormemente de nuestro propio sistema solar. El profesor Willy Benz ha combinado observaciones y modelización. Desde el punto de vista observacional, el profesor Willy Benz está fuertemente involucrado tanto en el desarrollo de misiones espaciales y en instrumentación para telescopios en tierra, con el fin de estudiar los objetos tanto del sistema solar y detectar y caracterizar exoplanetas. Lidera la misión de tipo S de la Agencia Espacial Europea, conocida como CEOPS, y que se lanzará en 2017. Esta es la primera misión que la ESA realiza de este tipo y lo que llevará a cabo es la caracterización de exoplanetas que son del tipo supertierra, son un poco más pesadas y más grandes que la Tierra, alrededor de estrellas brillantes. Desde la vertiente teórica ha aplicado modelos hidrodinámicos al estudio de aspectos esenciales en la formación de exoplanetas y su evolución. En particular, ha hecho estudios de acrecimiento de planetesimales con el fin de formar grandes planetas del tipo de la Tierra, y uno de los aspectos fundamentales a la hora de comprender los sistemas planetarios que vemos en otras estrellas es la migración de planetas. La existencia de planetas gigantes cercanos a las estrellas es muy difícil de explicar si uno utiliza el sistema solar como ejemplo. Esto lo que ha producido es que se genere un conjunto de nuevos modelos que permiten llevar a cabo esta explicación. La conferencia que hoy el profesor Willy Benz impartirá sobre cometas y planetas y los extraordinarios resultados obtenidos por la misión Rosetta de la Agencia Espacial Europea es un claro exponente de cómo el estudio de los objetos del sistema solar pueden contribuir de manera fundamental a entender la formación y evolución de los planetas. Así que, dada la introducción, le doy la palabra al profesor Willy Benz.
Thank you. Okay, first of all, thank you for these kind words. I'd like also to thank the Foundation for giving me the opportunity to speak to you about comets and planets. And then I apologize not being able to tell you this in Spanish, but I will do it in English. So the title of the talk is Comets and Planets. And I could not resist in showing you a picture of a comet because these are the pictures we know comets from. This is a picture that was taken in 2009 from the Paranal Observatory in Chile. You see here the 8.5 meter telescopes, and you see here the comet that is huge over the whole southern sky. And I was there at the time, and it was really like that. It was absolutely fantastic. So, except by being beautiful in the sky, you may wonder, why comets? Why should we bother about comets? Well, there are a number of things we need to learn about comets. We would like to know their composition. We would like to know their properties, the material properties, their shape, their orbit, the families. These objects come in families. And the number statistics. Which comets come from where? And with this information, we hope that we can then get some clues about the formation of our own planetary system, our solar system. Now, I work mostly on this side. I'm not the one that does make the measurements. I try to use what people provide here to get information about the formation of the solar system and planetary systems in general. Now, if you want, you can look at this like a detective story. It is something that you have evidence, people do some measurements, you collect some data, and then you do some serious detective work, and you try then, in the end, to reconstruct what has happened a long time ago. And it is as difficult as normal detective work. It's only on TV that it works in 45 minutes and the crime is solved. Here it's much more complicated than that because it takes 4.5 billion years of history to trace back, and you have only very few clues to trace back this history. And sometimes the clues are confusing, sometimes there are error bars, we measured the wrong thing, a thing didn't work, and so it is complicated. But nevertheless, we try to reconstruct what has happened. Now, you can ask the second question is, why are comets the good object to study to reconstruct this history? And in order to understand that, you have to look a bit at the life of a comet. So I draw a time axis here that will give you the lifetime of the comet. First, there is the birth. Birth of the comet happens during the very early stages of the solar system, during the first few million years, maybe out 200 million years. And then, and this is why we are so fortunate, these objects are stored in the freezer. For 4.5 billion years, they are mostly left alone out there, far away from the sun, in the cold. And it's just like at home. If you store something in the deep freeze, you can get it back later on. It's still as it was when you put it in. And so here it's the same process. We go get these relics out of the freezer and look at them and try to infer what has happened. And of course, when we see them, we can't really go get them. They're too far. They come on their own. And when we get them, then we have this, on top of everything else, this magnificent display that we know as comets. Now, because the years and the period of time here are kind of long, let me scale this. If we say the comet has been stored in the freezer for 1 year, then the formation time is just a few days, proportionally. And the time we have available to study them is just a few minutes. So that gives you a bit the time sequence between, the making of the comet, the time it spent in the freezer, and the time we have available to study them. Now, let me start walking you through this comet lifetime, and I start with the end. I start with the display, because this is the thing we know. Here is a comet, and I'm not going to do much of a nomenclature, but I will just tell you that a comet is what we see most of the time, when we can see them with the naked eye, is this huge tail that ranges several hundred thousand, up to 1 million kilometers in size. This is the first picture I showed you that fills the sky. And then you have a coma here, where the tip of the comet is. The sun is to your left. Here is a coma, which is big. It's 50,000 kilometers. But basically, this beautiful thing hides the most important object that you are interested in. All this is gas and dust that escapes from the central object in the comet, and this is the nucleus. This is a solid part that hides in this coma, 50,000 kilometers inside. This is 2 kilometers inside. So it's a tiny little thing. Comets are a few kilometers in size only. And they're hiding in this huge thing, and they're creating this huge display because they evaporate. This gas is coming out of these objects, and it's being thrown out in the solar system and illuminated by the sun, and that's what you see. But in the center, in the heart of this comet, sits a nucleus that's not much bigger than a few kilometers. Here I have a family album of all the comet nucleus that have been visited by spacecrafts. That's why we have pictures of the nucleus. So you see, you have the most famous one, Comet Halley, up here, 15 kilometers. And then you have all the other ones, the one you saw before. And of course, one of very famous one in these days is this very strange name comet. Nobody can remember. Churyumov-Gerasimenko, which is the name of the Rosetta comet. So here you have the family album, and as I tell you, is you first collect the evidences. And so you send your expert team to the object. In our case, it is the Rosetta spacecraft, which went to investigate the comet. And this sort of funny bird is almost like an albatross, very huge wings here, which are the solar panels, each of them being 14 meters in size. And the body of the spacecraft is just 2 by 2 by 1.8 meters in size. This is the mission. And what's absolutely fantastic about this mission, and quite unique, is if you overlay a timeline here. And you ask yourself, you look at when it happened. The idea of a rendezvous mission to a comet came in the mid-80s. It was sort of synchronous with Halley's passage. That sort of triggered enthusiasm of everybody for comets. And then it was selected as a mission early 90s by ESA. It was then built, launched in 2004, and then it traveled 10 years to reach the comet last year after 10 years of travel. Billions of kilometers later, it arrived there. So you basically have 30 years. It's a scientific project that lasted 30 years from the concept to the first data that arrive. Most of the people that started the project are retired. It's a new generation that works on the results. And that new generation has received the documents to say, if you push this button, then it happens this, but never touch this button, and so on. So there's a whole translation of information that had to go through 2 generations over these things. Now this, I'm not going to go into the detail. The orbiter itself has 13 instruments. The lander has 10 instruments. And here is the journey, the voyage of this comet. You have here the 4 inner planets, Mercury, Venus, the Earth, and Mars. And I have indicated the period of these planets around the sun. And you have this trajectory is the trajectory of that famous comet here. I'm not going to pronounce it twice, with a period around the sun of 6.5 years. And so the thing was launched in March 2004, and now we can follow the trajectory of the comet, of the satellite. It's the white line here. You see, it goes once around the sun. It meets first with the Earth, got the gravity assist, because the difficulty, you see, the comet is far away. You need to throw the satellite out. Second, then you have a Mars assist. And then you go again around a slightly wider orbit. You have a second Earth gravity assist here. And then the first science target came, is the encounter of an asteroid. I have a picture here of this asteroid Steins that the comet, the satellite met. Then a third gravity assist. And this one was a good one. Now it's being flung out here on its way to the comet, which is here. You cross another asteroid, make a pretty picture, and you continue on the thing. Now here you got into deep space hibernation because things take time out here. And so you see, it was carefully aimed at this little dot here, and then it was woke up out of hibernation, and then thereafter was the rendezvous maneuvers, and then the famous arrival at the comet. Shortly thereafter, the start of scientific data taking. A little bit later, the famous episode of Philae, the launching of the lander. And now it continues, and as the comet nears the sun, the tail develops, and the closest approach will be this August to the comet, to the sun, and then the thing goes away, and the mission will end by the end of this year, the nominal mission. If everything works fine, I'm sure they continue following the comet. But this is sort of the plan. This is, in a nutshell, all what happened and will happen in the future. And I'm sure you all seen the famous pictures of this comet. And here's one. It was a big surprise. We knew that, comets are, we had previous images, so we know comets were not spheres. That we knew. But we didn't know they could look quite that extreme. So you have here two lobes. The main lobe here called also the body, and the head here, and you have the dimensions, and this thing rotates around this axis in about 12 hours. So it's a fairly complicated object. But this is a shape model. This is not a picture. This is a shape model they'd made out of the pictures. And out of that, you can get a volume of this object. You can get the mass out of this object. And especially, you can get a density, a mean density. And this mean density tells you what it is, to first order at least, gives you a first indication what it is made of. Water has a density of 1 gram per cubic centimeter in these units. This has a density less than water. That means this thing floats on water. If you put it on water, it floats. Right? Rocks have a density of 2.33 grams per cubic centimeter. So even though it looks like a rock, it is not a rock. It is much lighter than that. It is even much lighter than ice, water ice. And so this led people to conclude that this object is more than half empty. There is a lot of voids in the comet. We don't see them because on the surface, there is a surface with dust and things, but you don't see inside. So one of the big challenges of future exploration would go to see inside these objects, to see how it looks. For the moment, we can look at the surface, but we surely would like to look inside. But from these measurements, we can already say that what we will find are holes, porosity. We don't know if these holes are big or very small. So this would tell us how these comets were made, if they were sort of brought together by big rocks or assembled from dust grains that will change the size of the holes inside. So this is one of the things we learned now about this comet. And by the way, we had this knowledge already for a number of objects in the solar system. They are asteroids. They also have very low densities, indicating they too are porous. And that again tells us stories about how these objects were built. Now then, I couldn't resist by showing you pictures. You know, these are things, it's absolutely fantastic. I mean, look at the details you see here. Look at the quality of the pictures here. I don't know, I said this morning to someone, I don't know if you remember what you thought when you saw the first picture, right? I mean, everybody went, wow. Really, this was not what we expected. So this is not the very first picture. This was taken not so long ago when they flew at 20 kilometers. And the size of this picture is about 3 kilometers times 2 kilometers here. And you see this. It's just astonishing. Then the famous Philae came and was dropped in November on the comet. And it came down, you know, it is hard to land on a comet. First of all, you saw the shape, right? First surprise, the landing, it's not so easy when you see that shape. You have to find a suitable landing. This thing is rotating. Everything is happening at the same time. So it was really a challenge to land these things. But nevertheless, it was attempted. And it went down and touched down the ground exactly as foreseen. Except the harpoons didn't do their job. Because the thing, you see, this object is so small that you virtually have essentially no gravity. So when you touch down, you bounce back, but nothing takes you back again, or very little. And so the idea was, at touchdown, you would fire harpoons in the ground, and at the same time have a little rocket on top that would make sure you anchor yourself in the comet and don't jump out. And this didn't work as it should have. There are many, many, many things that could have gone wrong here. And this was one little thing. And it was not even that catastrophic because the comet bounced, but it didn't, and that was the fear of everybody, bounce away back into space. Right? But that was not the case. The shock was smooth enough and the energy absorbed enough so that the rebound just took the Philae about 1 kilometer high up and drifted and landed here, and then it bounced again and landed there. And then it pretty much stopped. So you can look at it as a positive thing. There was always, you know, it didn't work and so on. So you can look, the glass is half empty. Or you can look at it the positive way with the glass half full. We landed 3 times on the comet. So this is, you know, this is the positive thing about this. We didn't do it just once, but 3 times. Now the problem is it's here, it's sitting here, and we have not been able to see it so far. It is here you have the landing, the ellipse where people believe it is. It's located here now. But it hasn't been sighted yet. It hasn't been sighted yet, and there has been no signs, no signal coming from Philae that I know of so far. The problem is the lander had the battery for 3 days, and the 3 days are over. It had solar panels. The solar panels would have kept it alive, but unfortunately, you see, it's in the shade. So there is no sun on the solar panel, and therefore Philae is just sleeping and waiting to get into the sun. So we're waiting until the sun shines here, and hopefully Philae will come back to life. So in the meantime, here's this sort of a selfie from Philae, where you can see one of his legs here, and that's sort of the environment in which the lander has been stuck. Now, we go back to the composition of the comet. There's a lot of data that are coming from the orbiter, and there's a lot of things that are happening. And I'm not talking about everything. I will basically be talking about the thing that sort of is useful to my purpose, the formation of planets. So here you have the comet, and you can see here there are jets of gases streaming out of this nucleus. And you have the orbiter that orbits this nucleus, and on board this orbiter you have what's called mass spectrometers, which capture this gas and analyze its composition. So obviously this thing is not as good as having a lander that measures the composition on the spot, because you don't know if everything is being ejected here. You don't know the fractionation that occurs in that process. But you can at least measure a lot of things. And one thing people were always interested in knowing is the water. Is there water on these comets? And what other kind of ices there is? And so here's an example of a result that came out this year, where you have here the comet. And at each of these moments, this mass spectrometer was making measurements. And you see up here what this instrument have seen. The yellow line is water. The blue line is CO2, carbon dioxide. And you can see that the composition, or whatever the mass spectrometer measures, depends on the orientation of the comet. Here in the neck, it sees about both equal. Here there is more water than CO2, and so on. So depending which part of the comet you're looking at, you're seeing a different composition. And the conclusion of this is that the comet is heterogeneous. It's not a nice ice cream that you can buy, like this, nicely mixed, smoothly mixed and homogeneous. It's sort of a bizarre structure with a lot of heterogeneity. Here again, it tells us about something about the formation of these objects. But we know there is a lot of water ice and CO2 ice. And this was, by the way, known a long time ago. This is a famous astronomer, Fred Whipple, that has invented this idea that comets are what he called dirty snowballs. So really snowballs mixed with dirt. And so his idea was you had ice and all sorts of ices, and on top you have a layer of dirt. Now, turns out that it may not be as easy as that. Here you have our famous unpronounceable comet here, and it's still the idea that there's a lot of ice in here, but exactly how much compared to dirt there is being debated, and whatever else there is also being debated. So we're sort of back to sort of asking ourselves how much ice versus dirt there is. Note that this proportion change with time, because the comet loses gases. This makes these tails, and it loses dust. So the ratio, the mixture between the two changes with time. So it also depends on the history of these objects. Okay, so now water, as you know, is composed of 2 atoms of hydrogen and 1 atom of oxygen. But from time to time, 0.015%, a hydrogen atom is replaced by a deuterium atom. Deuterium is an isotope of oxygen that has, of hydrogen, where neutrons is together with a proton in the nucleus. And that changes a little bit the water, makes it a bit heavier, and you can measure that. And on Earth, in the ocean water, we measure this ratio of deuterium over hydrogen to be this 0.015%. Okay? And now the idea is to use this ratio of deuterium to hydrogen to trace back the origin of the water. Question is, where does the water we have on Earth come from? Is the water coming from comets? Is the water was there all the time? It was part of the formation of the Earth. Did it came later? Where did it come from? Water is an important thing. Without water, there is no life. And so looking for water is looking for the conditions that are suitable for life. So it is an important constituent. As you know, people have been looking for water on Mars. People are looking for water everywhere. So the question is now, is the water that we have on Earth coming from comets or not? We know that on Earth the D/H ratio has this value, so we go measure the deuterium over hydrogen ratio in many different objects and see which one have the same ratio as on Earth. And this is a famous plot that just got published also this year. You have this 0.015%, the Earth's value, it's this line here. And you see the comets are here on this side of the picture. And we have these set of comets. They all have an enrichment. They have more deuterium than hydrogen than the Earth. Except for one of these Jupiter family comet, this Hartley 2 comet, that seems to have exactly the same value of the Earth. This measurement here was made in 2012. So if you go look at the literature, the newspaper, and the press releases at the time, you will find everywhere that, Jupiter family comet delivered Earth, the water on Earth. Problem solved. And here comes Rosetta, and here is the measurement. Wasn't as simple as that, as usual. This comet is much more enriched than even some other comets here. So, at least, but that we knew, this comet wasn't the source of water on Earth, but the comet in that family are apparently much more heterogeneous than what we have thought, and therefore they cannot be the main source for delivering water on Earth. Okay, so this is not. Now, the question where comes the water is still open. You see, there are other objects here, like chondrites, that have things that look like water. Chondrites are meteorites coming from the asteroid belt. So they are now, the trendy thing is to look for water in the asteroid belt. That's the probable, the next suspect, if you prefer, on our list of things to look at. Okay, now I've tried to summarize a bit some of the evidences we have. Now I would like to say a few words about how planets form so that you can see then the connection between these comets and what I've talked about with the formation of the solar system and planets in general. So planets or planetary system form, it starts with a gravitational collapse of a gas cloud that forms a disk-like structure that evolves, out of which planets are growing, and at the end you have a planetary system as we know, our own, and by now we know many others outside the solar system. So, if you want, it is in stages, it goes through like this, and we even have pictures, astronomical pictures of various elements along this sequence. You can see some of these disks. You can see debris disks here when the system is clearing. We have astrophysical evidence that this sequence is correct. We do not see our own history because the solar system is past. We cannot go back in time. But we see other systems, and we can figure phases during which our own system, would have had to go through as well. So we can see some of these things. The important thing is these disks. And now a disk is schematized here, where you have the star in the middle, and then you have this disk. Now is the side view of the disk. And it turns out, because the sun is very hot, that the temperature of this disk decreases as you move outwards. And you have here typical, it's very hot in the center, 2000 degrees. It's getting sort of nice and temperate at 1 AU. Right? It's not by chance. It's just where we are, because we don't like it too hot and we don't like it too cold. So it's just about right. And then when we go further out, it gets very cold. And now, depending on the temperature, different element can condense and become solid. Very close in, you have metals and rocks. As you move out, you have water ice and other ices. And the further out you go, you have more and more of these ices that condense. And I showed you this dirty snowball model and the content of CO2 ices and water ice. So we know that comets must originate from these outer regions of this disk. If they formed, they must have formed out here, because in here there would be no ices in the comet. First conclusion, right? These objects are formed however which they form, but they are formed outside here. So how is this formation working? So again, the time axis here, and the blue part of this arrow tells you that there is gas present. The gas disk is still there, and at the end, you don't have the gas anymore. The disappearance of the gas occurs sort of 5 million years typically after the formation. 5 million years later, the disk of gas clears. So you start with dust. It's a construction game. The idea is to use the dust that is in the interstellar medium, that is everywhere, and to aggregate the dust in bigger and bigger elements. First thing are planetesimals. These are objects a few kilometers in size. These are exactly the size of comets. So somehow you take a large amount of dust grains, you make some of those. Those then aggregate to form what we call embryos. Now, there are some new theories that say these dust grains do not agglomerate to make those, but they directly become big as that. And I show you an example later on. And then these guys erode or break and create the smaller ones. You see? So if you follow the dashed line, you conclude immediately that these little objects, the comet-like objects, are either an agglomerate of dust grains, or they are fragments of bigger things. They have been once part of bigger things. Okay, so then these objects here, they are still in the gas, and they're starting interacting with the gas. There is some gravitational interaction between this body embedded in the gaseous disk. And if they are very massive, they even create gaps. You see here is a Jupiter planet inside a disk of gas, makes a hole in the disk. And then you form Jupiter out of that. It accretes all this gas. And building a giant planet takes roughly 10 million years. If this embryo here doesn't grow enough to become a giant planet, it remains a small one like the Earth, and that takes about 10 to the 8 years. It just sits around trying to grow but cannot. And in the end, it terminates by sort of a smallish planet like Venus, Earth, Mars, and so on. But this one was formed before, so Jupiter has enormous importance in shaping the rest of the solar system, in particular these small elements here. Let me say a few words about how you can grow these planetesimals. Again, these are these objects a few kilometers in size that are of interest to us. First of all, you need to know is that the gas and the solids don't orbit the star at the same speed. The dust and the solids go faster than the gas. And therefore, if you want an image, is you solids see wind, because they don't move with the gas. They see this wind blowing at them all the time. And as a result, they are slowed down. It's like when you bicycle, right? When you go on your bicycle and you have wind blowing against you, you slow down. Most of us slow down. There are a few champions, they don't slow down, but most of us slow down. So they get this headwind and they slow down. And if they slow down, they move inwards. And they eventually fall into the sun. And this is not good for us because they don't make planets. So how do you make the bigger things? Then you start with these dust grains. These dust grains stick together due to surface effects. We call them in the jargon van der Waals forces. But they are surface forces that make these dust grains stick. Then you get millimeter sized and you try to build them by sticking them together to meter size. Now, we don't know how that works. You can try to go in your backyard, take two rocks, 20 centimeter, bring them together, and see if they stick. Generally, they don't, right? So it is not so easy to understand how you build these objects, and we're still looking for the glue. The missing piece here is the glue that makes these smaller objects stick together. Once they're big enough, it's gravity is the glue, and gravity will hold them together. But in the meter size, it is difficult, and I don't want to dwell on the number of things. But the first thing is to concentrate these dust grains in different mechanisms. And for very small particles, you can have turbulent eddies. For intermediate-sized particles, dust grains, 1 to 10 meter dust grains. Imagine a 10-meter dust grain, right? There's a particular dust grains. You can have different mechanism here, right? But you know it from own experience that dust grains followed gas motion and tend to cluster in some very special places, right? Under your bed, for example, and different things. These dust grains cluster, follow the gas. They move around with the gas and get together and cluster in these different areas. So now we can show these motions here. We have here a disk with a star in the middle, and here's a little cube that I cut out, and here's this little cube. And you're going to see the simulation, what's happening in this cube. There is a mixture of gas and dust. And you will see that this dust will collect itself in structures. Let's start and seeing what happens. Takes a little while until action starts here, until something happens. Let's see. Yes, now you see that it concentrates the dust. This turbulence that concentrates, it's called the streaming instability. And we experience it in our daily life when you see these things. The one, they cluster like this because you reduce friction, you reduce gas drag. And the one that are in the back here doesn't have to work as much as the poor guy in front, and that's why they change periodically to go faster than the single cyclist that gets caught up all the time when they do this. Okay? And in this area where the dust concentration has been going on, you can increase the dust concentration by a factor 100 or 1,000. You can really collect it. It's a super vacuum cleaner. You really concentrate the dust enormously, and then these entities here, this concentration of dust can form these first big objects, the first 10 kilometers or something, without having to go through this sticking meter-sized rocks together. Okay, you concentrate the dust and make the object 10 kilometers inside directly from dust concentration. And then the shape of comets, again, here it is. Now, in these very early days, there are no big planets. The velocity of this small object is gentle. Everything moves gently around the sun. And you can see that if you have such a gentle collision, things come back, and then they stick. And then you stop the movie just right. You blow up. And it looks very similar, right? So you can really build these kinds of two-lobe structures from these kinds of collisions. Of course, you can also, and that's sort of the competing theory, you can build this structure by erosion. And so we still don't know exactly which is which. But this is erosion, and we know that erosion works, right? We see funny structures on Earth that are the result of erosion by water, by wind. This is a thing in the Sahara. desert that's eroded by wind. And all these things happened there. So this is an open debate, what creates the shape of this comet. Now, let me say a few words on the storage in deep freeze conditions. I have to do something awful, is to show you this diagram. Just to define two little things. Now, don't look at the detail because then you leave the room. I just want to tell you that comets, planets, and everything that moves in the solar system basically moves on ellipse. You know, this is sort of what Kepler has invented. Here is an ellipse, and an ellipse is characterized by a number of quantities, but the one of interest for us is the size here, this quantity A, which is called the semi-major axis, and the eccentricity is the departure of the orbit to a circle. See, this is elongated, and this elongation is measured by a quantity called the eccentricity. If it's 0, it's a circle. If it's 1, it's a line. Okay, and then the other thing is the little inclination here, this angle I here, that tells you if the orbit is in the plane or not. That's all you need to know. And then here are the comets, the known comets. Here is this semi-major axis, so the size of the orbit, if you want, the radius of the orbit, in astronomical unit. 1 astronomical unit is the distance Earth-Sun. Okay? So this is 10 times the distance Earth-Sun, this is 100, this is 1,000, this is big. Right? So and here is the inclination of this orbit, if it's in the plane or not. In the plane is the plane of the planets. And you see, they are here, the Jupiter family comet, as we call them. They are the ones down here. They are characterized by being very close to us for comets. That's why they're called Jupiter family comet, because they're near Jupiter. Then you have the Halley-type comet, and then you have the very long period comet. Long period because, you know, they're so far, their orbit radius is so big that it takes them a long time to go around. And what you can see is just simply a huge difference in inclination. These Jupiter family comets tend to have small inclination, and everything else has very big inclination. By the way, our good old comet here, 67 CG, is one of the Jupiter family comet and is down here in that corner. Now, these here, this line here with all the dots, are all the comets that have period longer than that. And that was already noticed in 1950 by Jan Oort, who noticed that the comet peak at very big semi-major axes. And out of that, he deduced that there must exist a comet reservoir far away, and that reservoir is now called the Oort Cloud. Okay, so out of a little curve drawn by hand at the time here, you know, he got very famous. He did many famous things, I must say. But this was one of the things. So that's what his discovery was at the time, 1950, and there must be this comet reservoir a large distance. So the picture of our solar system with these reservoirs is as follows. Here you have the sun, you have a distance axis. Here you have our planets, some of them at least, and then here you have these reservoirs. The first one, which is this relatively thin disk here, is called the Kuiper belt, and out here you have this Oort cloud. And if you make sort of an inventory, you realize that this Kuiper belt was much more massive in the old days. We basically lost 99% of all the objects there were out there, for some reasons. I've come to that. If you want more a three-dimensional view of all this thing, here it is. Here is the inner solar system with the Earth, Mars. Then you have the asteroid belt. Then you have Jupiter, Saturn, Uranus, and Neptune. Here you have this Kuiper belt and the scattered disk. All this region is called trans-Neptunian objects, all these objects. And all that sits in here in the middle of this huge Oort cloud. Okay? And the radius of the Oort cloud goes so far that it goes maybe 10, 20% of the distance to the next star. So it goes very far away. Now, how do you do these things? Well, you have to play pool, almost. When a small object encounters a planet, things happen. I will just play pool, cosmic pool here. Here you have the sun, you have the distance, you have the Earth, you have Jupiter, and you have Neptune. Now, these objects go around the sun at the given velocity. The further away they are, the slower they go. The Earth goes around the sun 30 kilometers per second. So we go fast. Jupiter only goes 13 kilometers per second, and Neptune goes 5 kilometers per second around the sun. Now, you can ask yourself, if I want to escape from the sun, how fast do I have to go? You see this Oort cloud, this huge cloud, is sort of almost away from the sun. So you can ask yourself, what do I need to get for velocity to go that far? And nearly get lost. Well, you can plot it here. If you want to leave the solar system from the Earth, you need almost 50 kilometers per second velocity. If you want to leave it from Jupiter, you need 18. If you want to leave it from Neptune, you need 7.7. And luckily, you realize that the orbital velocity is smaller than the escape velocity, right? That we know the planets are still here. So that works. Physics is always reliable. So this is okay. Now, you can ask yourself now, if a small object passes by, you remember in the trajectory of our comet, we did this gravity assist. We pass by planets to get a little kick. Then you ask yourself, well, if I have a little object passing by the Earth, what kind of a kick does it give? So here I made this little calculation for you. If you pass by the Earth, you get an extra kilometer per second. You pass by Jupiter, you get 3 kilometers per second. You get to Neptune, you get 1 kilometers per second. For an average encounter, of course, it depends how close, how far, and all these sorts of things. So, now, what I want you to realize, and the reason why I tell you all this, is that these are the mechanisms that shaped, that sculpted the solar system and made sure these comets that were formed in the icy region, sort of around here, get kicked out so far and put in storage. This is a mechanism to put these objects in the deep freeze storage. Is these encounters. And I can show you here a simulation. This is a dramatic one. But this is the road we are going to. This is a projection of the solar system seen from above. You have here the orbits of some of the major planets, in red Jupiter, in white Saturn, in blue Neptune, in purple Uranus. And you have the dimensions here, and the green stuff are little objects, cometesimals, little objects that orbit the sun. Now, for you who know your story, you will have realized this is not the correct solar system. In the real solar system, Neptune is further out than Uranus. And the orbit of Neptune and Uranus are much further out than they are here. So this is a very different solar system. But this is the solar system we think was there at the beginning to explain this comet business, this comet reservoirs, this Oort cloud, this Kuiper belt, and all this delivery into deep freeze. Because if you do it with the solar system we have today, it doesn't work. So you're looking up for another solar system that makes the thing work. And this is part of this detective story. And this is a thing, so now we can let it go. Things will start moving. And you have time running on top here, you see, in millions of years. So we're up already at 100 million years gone by. And, things do what they are supposed to do. They go around the sun. And they go, and nothing much happens. The orbits of the planet wobble a little bit, so you think, it could be unstable, but it is not. It works fine. And then you would be tempted to turn off the computer and say, well, no. But then by chance, it's a weekend and you forget to turn it off. And this thing runs during the weekend. And then now you will see when you get to 880 million years what happens. Boom. The thing literally explodes because Jupiter and Saturn have crossed a resonance, a 1 to 2 resonance. And this has created havoc in the solar system. It has destroyed most of these asteroids or Kuiper belt objects or comets you had out here and thrown them out at large distances, some of them inside the solar system even. And it has, notice now, the planets are in the right order. Neptune is the one further out, and Uranus is inside the orbit of Neptune, and the distances are correct. Now Neptune is around 30 astronomical unit. So the thing you need to sculpt these comet reservoirs, and you need some event like this. And this event, by the way, does for you a lot more. This is a good thing. You know, you buy one and you get many. It ejects the Kuiper belt. It explains the late heavy bombardment, why we do have so many craters on the moon. The Trojan satellites, the resonance, and many other things that I don't want to go into the detail. But these are the key elements that this model explains. This model was proposed in 2005 by a set of 3 papers from people coming from Nice Observatory in France. And that's why it's called the Nice model. And it's, you know, in English, it's a nice joke because it's a nice model. So that is, it is the purpose of this thing. But the bottom line that I want you to remember is that it was very different in the early days. And you can trace back there because you study these little bodies. Now, it can get really complicated because planets also interact with the disk. And I have here a simulation of what happens. This is a top view, this is a side view of a planet embedded in a disk here. And the planet grows from 30 Earth masses to 300 Earth masses. And what you see here is how the disk and the planet interact. And you see all these funny structures. These are resonances. These are concentration of gas at very peculiar places in the disk. And the bottom line, I mean, why is this important? Why I'm showing you this is because at the end, here we are now a Jupiter mass. You see, you have now created a certain number of signatures in here. First, you have this gap. And the other thing is that you have these very funny shapes here. Now, I said this is a concentration of gas. These concentration exert forces on the planet. These forces are not central. That means there is a torque. No students like that. Physics students like torques. Don't worry if you don't understand the details of this. But it just means that you need these things if you want the planet to change its orbit, because a torque changes the angular momentum of the planet, and this creates migration. So planets don't stay where they are. This is one of the big lesson we've learned from the exoplanet, is the planet we see today have not been where they are today in the past. I showed you one example before. There are other examples, and the wild one is sort of the continuation of the model that I showed you before. Imagine here, this is sort of the latest twist to this thing. It's called the Grand Tack model and puts all the pieces together. And again, I mean, you have to realize this came to be because of comets and small bodies and the dynamics of all these small bodies. Here is a system that forms early on. You see, this is something that should look like the system, the solar system eventually, but it doesn't, because we have Jupiter that is inside 4AU, then we have Saturn, we have Uranus, we have Neptune. The blue little things are comets. that is small object containing water, and the yellow little things are asteroids, that is little object containing only rocks. Right? Now all this sits in this gas disk that I showed you before. All this creates these filaments, these structures, exert these torques, and as a result, Jupiter migrates inwards. As it migrates inwards, it creates, it clears this asteroid belt here. It goes all the way, inside to where Jupiter was once, if you believe this, was once closer to the Earth than Mars is today. But it was before the Earth existed. So, lucky us. But it helped the creation or the formation of the Earth. Now, Saturn here was growing and at some point decided, well, better catch up. So he went back and followed Jupiter on its way in. And by that now you can see that some of these blue icy things have come in the inner parts here. Because the water could not condense in the inner part because of temperature. So it condensed outwards, but so this dynamical effect drove the water inwards. And then we go back a little bit. Jupiter and Saturn decided, that's it, enough of it, let's go back out. Now, it sounds like a magical trick, but it actually shows in the simulation that because of these torques and these structures, if you have these planets, at some point they go back out. The net torque is such that the planet goes out. And so they go out, and at some point you reach a situation that is like this, stable for a little while, until the instability that I showed you before kicks in 880 million years later. This is the initial condition of what I showed you before. This is building the instability. And then you go do what I showed you before, and you end up with what we know and love, our own solar system. Okay? So you may conclude that it is getting really complicated. And it's right. It is complicated. Now you can say, maybe it is getting so complicated that we may have something wrong. And the real solution is something much easier. I read that somebody said one day, this happened in the past when people thought that everything should move on circles. And because the circle is a perfect figure and everything should move, God's creation can only move on the perfect figure. And therefore, everything should move on circles. But then quickly one observed things that were not moving on circles, so people added smaller circles on big circles that was called epicycles. And they started adding those, and it was getting really complicated until Kepler came and said, it's all ellipse, guys. And then it was just one figure, and everything was clear, and then came Newton and explained why it was ellipses. And so that was it, right? So maybe we're on the wrong track. I don't know. That's why we study these objects, and that's why the story is not over, and that's why detective work doesn't finish in 3/4 of an hour like on TV, right? So I'd like to conclude with a few comments here. Comets are small in size, but they are important tracers of what happened in the past in the solar system. And they give us really good clues of what things, because they have been stored in this deep freeze and haven't changed for so long. The funny thing is, without comets, there wouldn't be planets, and without the planets, we wouldn't see comets. So there is a close link to these two, and that's why I chose this title for this talk, because the two wouldn't go without each other, which is kind of funny, because a thing like Jupiter, the size of Jupiter, it's not necessarily related with a small core of a comet of a few kilometers inside. What we've learned from the statistics and the dynamics and the characteristics of comets is that the formation time of our solar system was quite violent. There was a lot of things, a lot of dramatic dynamical events that happened in those days. And Well, this is what we try to learn, and the comets end their life for our pleasure in a final big grandiose display, and Rosetta was a key actor in trying to get most out of this display. Thank you for your attention.